The power of algorithm. Artificial intelligence and algorithms are supporting us in many aspects of our everyday life. On the other hand, heat treatment is a science that was building its traditions throughout centuries. How to combine a science with such a great legacy with the modern wave of technology? What algorithm has to offer to heat treatment world? These are the questions that will be discussed with our today's guest. Please let me welcome Dr. Emilia Wołowiec-Korecka, MSc degree in computer science, PhD and DSc degree in material science and engineering from the Łódź University of Technology. Welcome.
Lovely.
Professor Piotr Kura, again, a retired director of Institute of Materials, vice rector of Łódź University of Technology, and the founder and the board member in Hardtech hardening plant.
Hello.
Dr. Grzegorz Korpała, double diploma program between TU Berg Academy Freiberg and the AGH Kraków in field of material science and technology, PhD, and the leader of hot forming simulation department at the Institute of Forming, Metal Forming, Berg Academy Freiberg. Hello.
Hello.
So Professor Kula, the question, what does it mean, what algorithm has to offer to heat treatment world?
So, it's the very important issue. Let me support my answer by the short presentation. Presentation entitled Artificial Intelligence Tools as a Support for Vacuum Heat Treatment. I prepared this presentation together with Professor Emilia Wołowiec-Korecka, who has the great experience and knowledge and skills in this field. So, first, let me try to answer why vacuum heat treatment technology generally. Of course, everyone knows today that the vacuum technology offers the compact installation, is environmentally friendly, it offers cleanness, improved microstructures. So the vacuum technology is generally the good technology for a wide product range. So the important part of modern vacuum technology is vacuum or low pressure carburizing. Sikorsky developed this technology together with our research team for the long time, maybe 20 last year or more. So what is the basic difference between the traditional gas carburizing and the vacuum carburizing? The traditional gas carburizing is controlled by the carbon potential value. The carburizing gases are supported from the gas generators and the online monitoring systems based on oxygen probe keep the potential on the required level. This is the critical factor for the solving of diffusion equations, so we are able to control practically the development of carbon profile online. So the vacuum carburizing or low pressure carburizing is generally non-steady state process, so it's hard to keep and control the equilibrium. The question is what to do. Absolutely, the artificial intelligence tools are necessary to foresee, to plan the schedule of each vacuum carburizing process. So, a few words more about the vacuum carburizing to make more understandable that process. So, the heating to the high temperature goes at the inner atmosphere at vacuum, and the carburizing period is divided into several segments. Boost and diffusion, rich in carbon, poor or zero carbon. Consequently, the development of carbon profile goes at non-steady state boundary conditions on the surface, and it is the difficult issue to be dissolved using the traditional methods. Therefore, we built the algorithm, the special algorithm to plan to simulate the development of carbon profiles. For that, we developed the advanced artificial intelligence product. It is generally called SimVac, Process Simulator, and it is consisting of two moduli. The first one is the SimCarb to simulate the development of carbon profile during the numerous boost and diffusion stages, and the next stage is the SimHeart, and it is dedicated to simulate the austenite-martensite transformation in the carbon region or poor regions to reach finally the hardness profile in the surface layer in the case. So as you can see, it is very hard numerical challenge for that program. Therefore, because the surface concentration changes continuously during the process, we have a lot of phenomena which we should take into account during processing of this algorithm. So, therefore, the first issue was the development on the real physical model of vacuum carburizing. It should take into account dividing the process into the saturation and hold stages. It should additionally include the phenomenon of share of carbon deposit. Also, the carbide formations and dissolution is taken into account. The program is very clever, and it's able also to take into account the effect of item geometry, like, for example, different curvatures of details. It knows also the effect of alloy additives in carburizing steel. Therefore, in my opinion, it is very, very clever artificial intelligence tools which is consisting of knowledge of several generations of heat treaters inside. So, the very important thing is that the program works in real time. We don't have to wait a long time for the solution like at traditional FEM or computer fluid dynamics programs. It works really very fast. So, what the challenges were during the development of the SimVac process? The first and very important was to obtain the proper heat transfer coefficient values in high pressure gas quenches furnaces. The first approach we did using the conventional computer fluid dynamics programs. So the first approach was the estimation the chilling rate and heat transfer coefficient for the dedicated furnaces at dedicated pressures of inert gas, and then all this data have been confirmed by numerous experiments. So we are really very sure that this data describe very well the real phenomena inside of vacuum chamber. So finally, we described the relationships between heat transfer coefficients and time versus time for the fixed pressure of inert gas, and we introduced into the memory of this program this three-dimensional relationship of heat transfer average heat transfer coefficient, the mass of charge, and the shape and area of charge, and these two values describe very well the efficiency of heat transfer. The next important relationships are the digital CCT diagrams, continuous cooling diagrams. So we are able to foresee the efficiency of austenite, the martensite or austenite binary transformations at the stage of high pressure gas quenching. So finally, the program is very nice. It's very suitable for staff for lab. So the operator introduces into the program only the surface layer requirements, details of geometry, mass and area of charge, cooling gas properties. We use furnace chamber cooling efficiency, and the program's memory is processing of the following relations: hardness versus carbon content and cooling rate. It introduces the additional modifications from the steel database, and the cooling gas pressure we choose also, and the program automatically analyzes the cooling kinetics and carbon profile in the surface layer. So finally it offers the necessary hardness profile, and this is the goal in the heat treatment, especially at for low pressure carburizing. So as you can see, the accuracy of this program is very close. You can see the comparison of simulation and result and experimental results. Both these curves are very close together, so it confirms the good reliability of this SimVac SimCarb program. So the next functionality of the SimVac program is the special dedication for gears. Gears are the important group of low pressure carburized cases. So the program helps us to simulate the differences in the carbon profiles along the tooth profile. It is very critical factor, especially for very important customers. They expect the homogeneous thickness, homogeneous hardness on a whole tooth. Of course, it is impossible, but this program helps us to find the compromise between the hardnesses, between the thicknesses of this case. So the achievements in the heat transfer efficiency enabled us to develop the next artificial intelligence tool, namely the G-Quench Pro software. This G-Quench Pro software is dedicated especially for high alloyed steels, die steels, high-speed steels, generally tool steels, and especially dedicated for the large products like dies for forging, dies for forming, for injection casting, for injection of plastic. These are really usually the very massive parts. It's hard to foresee the proper chilling rate, the cooling rate, and its effect on the final microstructure. The program contains a lot of data inside. It contains the CCD diagrams for practically all tool steels, and it is the valuable support tool to control the difficult technological process, the quenching of large-scale, high-alloying steel dies. So the next step in our thinking was continuing of this issue, namely, if we are able to quench properly the large die. So, as you can see, quenching. The next stage should be usually tempering, the single tempering or double or triple tempering. The question was why not to replace the second tempering by nitriding, which would be carried out in the same chamber without discharging of the furnace. And of course, we developed the low pressure nitriding technology as the additional option for that process. And together with our team, especially together with Professor Korecka, we developed the software, CLPN software, that help us to foresee the proper parameters to reach the necessary microstructure of nitrided layer in the surface, especially the nitrided layers free of white nitride zone. So, of course, this program also was the great challenge, because also in this case the nitrogen potential widely used for the nitriding technology is further not descriptive for that process. So also here the process must be divided into the boost and diffusion state, rich in nitrogen and poor in nitrogen. But comparing to the carburizing, the problem is more difficult, because it is not one phase diffusion. There are several factors which influence on the development of nitrogen profile and microstructure. Therefore, our proposal was to apply the network of neural network to dissolve this problem, and to teach this neural network on the very large experimental base. So results were visible here. We are able to reach the proper microstructure. Only the dark layer without any traces of the nitrides on the surface on high-speed steels, like here, M2 steel, on the H18 steel, like here, and very nice the hardness profile obtained in this technology, and finally also on the D2 steel. No nitrides on the surface, only dark layer. So, summarizing answer on your question, not so short. So, this is the answer on the question: tradition or progress. Of course, the choice is also yours. The choice belongs to the customers. But in my opinion, the knowledge of customers plus the experience may be very well supported by artificial intelligence support. The present and offered artificial intelligence tools contain the knowledge of generations.
Well, that's really interesting. To me, it sounds a little bit like a sound of the future, but it appears that it is available on the market since many, many years, and it has a proven track in industry, right?
Yes, it's right. Absolutely so.
That's a remarkable thing. Thank you very much, Professor.
Thank you.
Another question to Dr. Wołowiec-Korecka. You are one of the creators of SIMVAC, right?
Right.
And somehow in your everyday work, you combine two words. On one hand, you are software engineering. On the other hand, you are material engineering.
That's correct.
Every software has got an algorithm inside. So please tell me, what's the difference between the algorithmist and the programmer?
Oh, it's a good question. And I answer referring to Polish legal status. So in Polish classification of profession, there are several groups of IT professions, including group number 251 called computer system analyst and IT programmers. And this group includes programmer profession as well as designer ICT systems, who we can call algorithmist.
Okay.
Okay. With all due respect to both of these very skill-intensive professions, a programmer is a craftsman. He creates code lines similar to bricklayer who erects walls of the building according to some plan. A vision of a whole system is a designer responsibility. He is a person who creates a description of all software components. So typically, the development project needs a group of programmers and only one designer. However, I should add, a designer or architect of the IT systems not work alone, really. Usually, his project is the result of his cooperation with group of experts in the field of the project. So this is the difference between these two professions.
Okay, so we can say that it is never a standalone work. It is always a work of a group of people.
Absolutely.
That are working. Okay. We heard a lot about the SIMVAC. We have a lot of knowledge that came from Professor Kula's side, but what actually is the SIMVAC and how does it work?
SIMVAC is a computer software for developing, predicting, and optimizing heat treatment processes. It has been developed in 2003 and still and is continuously improved. It's integral part of fine vacuum carburizing technology designed by Sikowori Group and Lodz University of Technology. As Professor Kula mentioned in his lecture, during calculation, the system takes into account many parameters like steel grade, geometry of elements, surface carbon concentration of the surface, or carburizing temperature. In the next step of the processing, the parameter of cooling medium is taken into account, which result in high accuracy of predictions of the result of experimental processes. But in my opinion, the really significant innovation of the application is its focus on economic aspects. It was tested that the demand of the carburizing gas is not constant, really, and actually decreased during the process, during the segments, during the saturation segments. So SIMVAC calculates the amount of gas the church can use in each saturation step and includes this information in his recipe. This operation allows reducing the amount of carburizing gas by up to 70%. So it's big goal, I suppose.
Yeah. We do have a film about the program, so maybe we can see it in action, right?
Yeah.
Hello, my name is Michał Bazel. I'm the Heat Treatment Technologist in R&D Department Sikowori Company. Today, I would like to show you how it's really fast to implement the low pressure carburizing recipe using this, and using SIMVAC on the computer. So please come with me and see what's happened. Okay, now I'm sitting in front of my laptop in the office, and I will show you in several steps how to use the SIMVAC simulator to create the most important parameters for LPC recipe. So first of all is to have a 100% sure that the furnace which will be do finally the recipe is the same like in SIMVAC simulator. So I check it right now, and for my simulation and for my recipe I use furnace name VP446, and the mixture will consist of acetylene, ethylene and hydrogen. Next is to use one of this icon. This is the process wizard. This is the process optimizer. Process wizard is dedicated for most advanced people. The process optimizer is dedicated for the beginner. I will use the process wizard. Okay, next step is to give a name for the process. Next is to choose the temperature, then the data after carburizing, I mean pre-cooling, the ramp of pre-cooling, finally temperature for pre-cooling and soaking time. And another parameters are pair of carburizing and diffusion and their times. Okay, click next, and now I choose a steel. Next is the geometry, cylinder, external surface, a number of radius. The next, and basic information about the charge area. I will use the automatic system or window to calculate my active area. That's the parameters for my example of a single piece, the quantity, and once again material. Okay, summary information about the charge. Okay, next, and simulation is ready to be run. Here we go, the curve of carbon. This looks not perfect, so I decided to do some modification using this icon. Process editor, everything could be or can be modified. So I decided to add extra 2 segments of or 2 pair for carburizing and diffusion, and I do this. Okay, click this button and do the resimulation. Very well. So now the curve of carbon looks much better. And so the last thing is to save the file which will be implemented to the recipe on the furnace. Okay, so main part of low pressure carburizing process is ready. Now I will implement it into the recipe. So now I'm staying in front of the furnace computer, and I will implement data from SIMVAC simulator into the recipe. So what I will do, find out the recipe, click edit, and here we have the almost ready low pressure carburizing recipe. Almost ready means that we have pumping, gas heating and partial press heating, the segments for the beginning, and the blower cooling, the segments after carburizing. Now I will implement the data from simulator. I click this icon, find out the proper file, click open it, and then choose the right position. Import. Here we go, everything is correct.
We heard a lot about the SYNVAC, but there is also a G-quench. What's the difference between SYNVAC and G-quench, and how does it work?
The name G-quench is abbreviation of words gas quenching simulator. So it's dedicated to simulate and control the hardening tool steers in the gas, also under high pressure. We've reduced the need of testing processes. So not includes carburizing technology, only quenching technology. During calculation, the process is simulated according to parameters defined by the user. The direct simulation, the direct result, is determination of cooling curve for a selected material under cooling condition. In combination with built-in digitized cooling transformation graphs, the curve provides information about the material's phases during processing. The final effect of the simulation is to determine the expected final hardness of the material. But at the same as the predictive functionality, the monitoring function of the actual hardening process were developed. In monitor mode, the program connects to the furnace who provides to G-quench information on how the chamber works in this moment. So as the result, a curve which is an actual record of the process is superimposed on the cooling curve determined by the simulator. So in this way, the correctness of the hardening process is verified in real time. And it's the main benefit of this program, in my opinion.
Okay. So we know that algorithm supports a carburizing process. They are supporting quenching process. And what's more they have to offer? I know that there is a zero flow feedback control system, and we do have also prepared a nice presentation about that. So maybe let's see it on the screen.
Nitrating is a thermo-chemical process in which surface of machine parts and tools are enriched in nitrogen. In high-temperature processes, an atmosphere of ammonia, surface diffusion layer of improved tribological, anti-corrosion, and wear resistance property is being created. Elements that undergo this process are mostly parts of machines and vehicles, such as crankshafts, gear wheels, camshafts, piston rings, valve discs, and nozzles, as well as tools like molds and drills. Created diffusion layer, depending on nitrated potential, can consist of eta gamma prim alpha, and alpha phase. During nitrogen processes in high temperatures reaching between 490 and 560 degrees Celsius, ammonia, when in contact with metal surfaces, decomposes into nitrogen and hydrogen. As a result of those reactions, the atmosphere in the furnace consists of ammonia, hydrogen, and nitrogen. Other parameters that determine its kinetics of growth of nitrated layer, so its pace of growth and phase structure, are temperature and nitrating potential. Nitrating potential is a quotient of molecular pressure of NH3 and H2. Zero-flow nitrating technology is a result of lifelong research of thermodynamics and kinetics of nitrating by Professor Leszek Małdziński. Its industrial version, however, is a joint success of teams from Poznań University of Technology and Seco Warwick from Świebodzin. Zero flow is the most advanced and yet most simple in operation controlled gas nitrating method. It relies solely on using ammonia gas throughout the whole process. Flow of ammonia is being periodically reduced to zero, which enables a precise control of nitrating potential and formation of designated layers. Offline Simulator is a computer software based on thermo-chemical and kinetic equations, as well as experimental research describing speed of growth and phase structure of nitrated layer and functions of temperature, nitrating potential, and time. Simulator determines values of those parameters that will result in obtaining designated layers. In offline simulator software, there's a possibility of setting process parameters by hand. Simulations results are presented as values of thickness of nitrated layer, as well as graphs showing change of parameters and layer thickness throughout the process's time. Weak spot of offline simulator lays in arbitrarily set values of heat-up speed of the retard and pace of nitrating potential reduction that may be different from its real values. These depend on multiple factors such as furnace's heating power, weight and surface of the load, and catalytic activity of retard surface, all of which are hard to determine. Online Simulator is an offline simulator installed in furnace's software that controls nitrating process based on feedback control. It calculates growth of nitrated layer based on real nitrating parameters and adjusts them in such manner as to achieve desired phase structure and thickness of occurring phases. This graph depicts simulation of process with arbitrarily set values of temperature, which for first stage is 490 degrees Celsius and for second stage 550 degrees Celsius. Heat up speed to first stage temperature is 20 degrees Celsius per minute and to the second stage temperature 1.8 degrees Celsius per minute. Nitrating potential in the first stage equals 10 and in the second stage equals 2. Speed of reduction of nitrating potential from the first to second stage value was set to 0.11 per minute. As a result, layer consisted of epsilon and gamma prime with thickness of 9.2 micrometers and diffusion zone of 0.22 millimeters was achieved. Time of process calculated from 450 degrees Celsius, so from the beginning of calculations until acquiring desired layer, was 7 hours. This graph shows a comparison between the simulation mentioned before and a process with lower speed of heating up and potential reduction. Presented on the graph as dotted lines are real values of temperature and nitrating potential. With lower speed of load heat up and slower potential reduction, the growth of diffusive layer is also slower. In order to receive exactly an identical layer, its thickness structure and effective depth, time of second nitrating stage was longer by 50 minutes and nitrating potential was reduced from 2.0 to 1.85.
we have seen zero flow feedback control in action. Professor Kula, do you think that in upcoming future, the nearest future, such kind of control system will be used commonly in the heat treatment world?
I think yes. So the zero flow process is the advanced kind of gas nitriding technology. Therefore, it is describable by nitrogen potential. So we are able to use both approaches to the monitoring, namely the offline and online. Offline is very good for the first approach of process parameters establishment. So online is very good to control the flow of the process. So it takes into account both the proper behavior of equipment and also the risks. If we have the problem with the process, we are able also to improve the flow of process to make the necessary corrections. So, in my opinion, this type of software is very valuable for the future applications.
Okay, thank you very much. During this panel, we've got also one more algorithm to discuss, and that is cycle coil annealing 4.0. Sometimes one picture is better than 1,000 words, so let's start from the video.
One of the key branches for the development of the world economy is production of aluminum, which consists of a number of stages, including heat treatment carried out with the use of industrial furnaces. SICO Warwick is a global manufacturer of furnaces for heat treatment of aluminum, including vortex furnaces, in which intermediate or final heat treatment of loads in the form of coils or foil coils made of aluminum and its alloy is carried out. In particular, stress relief and recrystallization annealing. Stress relief annealing is used when the material has lost its ability to deform due to rolling and the process has not yet been completed. As a result of stress relief annealing, a gradual, continuous disappearance of the deformation of the crystal lattice caused by the strain. As a result of recrystallization annealing, new grains are formed with an undistorted crystal lattice, as a result of which the tensile strength of the material reaches the minimum value and the elongation maximum one. Full recrystallization of the material completely removes the effects of cold work. In order to fully and continuously control the above-mentioned processes, it is necessary to know the temperature field in the section of the heated coil. For this purpose, SICO Warwick has developed a motor system called SICOIL dedicated to vortex furnace line, which is a part of the Industry 4.0 concept. SICOIL is a set of tools for the design, optimization and control of the heating process of aluminum coils. The main element of the SICOIL system is a mathematical model of batch heating, which enables the determination of the temperature field in the cross-section of the coil at any time in the process without the need to use load thermocouples. Mathematical model can be used both for process simulation and design, as well as real-time process control. Mathematical model as an online controller, in cooperation with the primary system of the furnace, simulates the current temperature field in the cross-section of the coil using information on the current conditions in the furnace's heating chamber and the parameters of the heated coil. SICOIL allows you to choose the location of the so-called virtual control thermocouples, the indications of which can be used to control and regulate the process. The screen shows the real-time coil heating curves. The black line shows the temperature of the furnace heating chamber measured by the regulating thermocouple. The red line, the highest temperature of the coil determined by the simulator. The blue line, the lowest temperature of the coil determined by the simulator, while the green line, the temperature indicated by the so-called virtual control thermocouple. The task of the automatic regulation and control system is to maintain a certain temperature excess in the heating chamber until the appropriate, safe temperature is reached at the virtual measurement point. and then to lower the temperature of the heating chamber according to a strictly defined relationship. Thanks to the applied procedure, it is possible to obtain the shortest possible process time without the risk of overheating the coil. The following advantages of C-coil system can be mentioned. No need to use and service loud thermocouples. Any choice of the location of the so-called virtual control thermocouples. The possibility of archiving data about the temperature field of each processed coil in the cloud. Possibility to optimize process time and energy consumption.
Dr. Korpała, you are one of the creators of SEC-coil coil annealing 4.0, is that correct?
Yes.
And for everyday job, you are dealing with modeling physical phenomenon in metal manufacturing. I need to write that down because this is a tongue-breaking sentence for
Understood.
me. For the process, a lot of parameters are quite crucial, right? Please tell me why the information about the annealing coil temperature field during the annealing process is so important.
Yeah, this video have already most of those questions answered, but the main part is let me explain why we do annealing first of all. As you have saw, we have a very clear surface of these coils of this material, aluminium, with different alloy types, and those alloys are cold rolled to this form. So we have a roll coil of different thicknesses of those strips. So by cold forming, cold rolling, we increase, of course, the hardness of this material and decrease so that the material will be brittle. And our customer, by such material, will not produce cans or car bodies without formability of those materials. So we need to put it heat activated processes to reduce hardening, to increase elongation potential, so formability. So that can be those alloys extremely good make into our end product shape. So for this processes, we use two mostly common processes. This is recovery, which reduce the hardening by simply dislocation diffusion, and recrystallization by reconstruct our internal structure of material, which we call it microstructure. Of course, this microstructure, to be completely recover and rebuilt, we need time. Of course, we can increase temperature and decrease our annealing time, or in another direction, we can increase time and reduce temperature. Of course, we have here the question of costs. Machine hour is not cheap, and we want to strongly increase the amount of coils which go through the furnaces. So reducing of time, it will be the best way to go. If we use SEC-coil program which calculate physically based models which are implemented in algorithm of engine in this program, we can make those temperature field, internal temperature field in coil homogeneous, to don't generate some cracks by forming by our customer. Of course, the most important thing here are phenomena which decrease effectivity of heat transfer in the coil. So the system is calculate heat transfer in two directions. This is the Z-axis direction and radial direction. Of course, we want to increase heat transfer in axial direction, because there we don't have many layers of our sheets. but of course we can use some pressure between layers to increase transfer of heat. That means we put our heat inside the coil, and the inside layers grow and push to our outside layer back. That means increase the surface which react by transfer of heat. So that's many different types of phenomenon which are needed to be taken into account to calculate real cross-section field of temperature.
Okay, thank you. Now from the other angle, from the R&D department perspective, what are the biggest challenges in working on a control system that based on Industry 4.0 in terms of manufacturing in metal area?
The main task of R&Ds, I think it's to collect data of materials which are needed to calculate such models. But if we talk about models, I think many different models. It can be empirical models, which basically are a very simple Avrami equation. We have also neuronal networks models, but they need a lot of data. And also, so we have a physical-based model, which use physical data like thermodynamic equilibrium calculation, but not only this, precipitation calculation, recrystallization in mean grind grow or recrystallization grow new products of transformation by austenite, like we have talked about austenite martensite or bainite. So there is a lot of phenomenons which are physical based, and we can describe those, but we need large set of data, and this is the main task. But for that, of course, we need the money. So as the R&D, we need to go to our bosses and talk about money. So the second task is to explain why these basic data are so important for the company for next 20, 30 years, because on this basic we can work in and innovate new technologies.
Well, the investment, such an investment, usually are returning after several years. So that's the big power of algorithm. Well, that was last questions from our panel of algorithm. Thank you very much for a nice discussion. I believe that algorithms are becoming a natural part of our everyday life, and they are becoming a powerful tool in the experience hand of heat treaters. They are not trying to steal any job from the specialists, but they are a powerful support for their everyday job, just to build a 21st century heat treatment shop. I believe I would be really happy if we could leave our guests with that kind of question. So what algorithm can do for us in our heat treatment world? Thank you very much.